and then see that what is the kind of understanding that we have theoretically and in terms of some kind of models. This is also very recent. The actual clear scientific methodologies have been applied only very recently compared to the human civilized, the age of the human civilization itself. So this all happened, we can say, roughly in the Middle Ages. And Newton's way of looking at the gravity was quite successful in various different terms. But then in last century, Einstein gave us a slightly different picture. In fact, in principle, it is completely different picture. But when you work out things, most of the things that Newton's gravity has given us, so will work out well for practical purposes in general theory of relativity as well. So there is no change in terms of, say, for example, planetary motion, etc. But underlying principle is completely different. In fact, that is what led Einstein to actually think about general theory of relativity, where Newton's way of looking at gravity or any other force was kind of action at a distance, that there is nothing to actually communicate this force between, say, Earth and Sun. But Einstein, in fact, Newton himself was also not comfortable with that, just that he did not know how to go about it. And many, I am sure, many scientists at that time was also similarly be thinking. But then Einstein gave a way around that and then said that you can actually think about gravity as something which the space-time itself is involved. And one of the consequences is these gravitational waves. For example, if some, in the picture that we have seen, what happens is that a violent kind of event, like the merger of two black holes, happens, and then some energy is released. It's like goes into the ripples in the space-time itself. This can happen only if the space-time itself is part of the gravitational interaction. Unlike in the case of Newtonian thing, where the space is just like a stage, it doesn't act. Whereas in the case of gravitational waves, it is the act. It acts itself. The stage itself is part of the action. So we have now ample evidence for all these things: gravitational waves, the black hole itself, and then there are this something called the lensing effect, where in Newtonian gravity you cannot bend light because the light is something like which does not have mass, whereas in the case of gravitational general theory of relativity of Einstein, it's possible because it's not because of the mass of this particle that it causes. Whatever has energy or moving, it has to move through this space-time, and if the space-time is curved or if there is any contour there or any changes there, then it has to follow that path. So basically that is what is happening in the case of light bending in Einstein's thing, and then we have ample evidence for that now. So going on to the next slide, we have put all these things together and developed a model for the cosmology, for the universe. So this is basically what is called the physical cosmology. And physical cosmology puts together general theory of relativity. And of course, to think about and talk about matter in it, we have to put in the particle dynamics, and then the cosmological principle, which is basically saying that it doesn't matter from where you are looking at, the universe looks the same, and it doesn't matter from which direction, it looks the same. So, according to general theory of, according to this cosmology, the cosmology that we have, this model that we have, which goes by the name of Big Bang cosmology also. So the universe actually started. It had some kind of a starting, and then that starting in the beginning, We don't know exactly the starting point yet. That is a singularity that is something which is not at all accessible at the moment. But very early stages of the universe has been speculated, and then some indirect evidences of that, etc., is there. And the physics, the cosmology actually has the model has a kind of a picture from very early times, and it is thought that in the very early stages, the universe was kind of in a hot, dense radiation or hot, dense energy which is packed in a small region. And then it expanded. The expansion means the space time itself is expanding. It is not like a fireball expanding in space. The space itself is expanding. That is the gravitational expansion. So the universe expanded like that, and then as it expanded, the energy density, of course, goes down, and then it cools, and then particles could be created. So the elementary particles were created at some very early stages like that, and these elementary particles were in a kind of a soup called quark gluon plasma. I will come to quark means the things that make the proton and neutron, the elementary part, basic elementary, very elementary stage of the particle is a quark, and of course electrons also. So at that stage, and then in from there it evolved as the universe cooled down further. Then there's elementary particles came together, quarks formed bound states called protons, neutrons, and other what's generically called hadrons, and electrons were of course there, but electrons were so very high energy energetic electrons, so that bound states with the protons or the nuclei could not be formed, and uh, because the energies are much higher, and it was actually again a kind of plasma state, but this is not the quark gluon plasma, but it is basically the usual plasma that we are familiar with, ions and electrons. So light elements like hydrogen, helium, deuterium, and lithium, etc. The nuclei of these elements were formed, and further on, after a long time, and then the uh, universe again cooled down further, and energy of the electrons were smaller, and then they actually could form the bound states with the atoms. So a lot of hydrogen atoms and helium atoms were formed there at that time. And then further on, just to cut the long story short, we have, when we look at now, it expanded into the present form, forming large-scale structures, many large-scale structures, including um, galaxies and galactic clusters. Okay, so let's go to the next slide where we have so the same thing said, but it's a more professional slide which I have borrowed from Particle Data Group, and this actually gives information about various stages of this thing, including the time scales which are included. So the Big Bang nucleosynthesis happened around 100 to 1000 seconds. Okay? And the first 3 minutes, in the way, is the is what this nucleosynthesis happened of the light elements. But then after that, a long time we had to wait, something like 400,000 years for the universe to cool or the universe to expand enough to cool the electrons down to where it could actually form the atoms. So that is where the atoms are formed. So in the next slide, we have this stage is an important stage in the universe. And then, so we have what's called um, uh, the photons, radiation was not always there. Particles were formed, but there was some radiation left out. And these photons in the plasma stage where there were no atoms but the nuclei and the electrons, etc. That plasma, it has very small mean free path, so they don't really they are kind of trapped there. They are not able to freely move around. But by the time the atoms are formed, then it is a neutral state, and photons don't interact much with the atoms in that way, and they are free to move and they're free to propagate. So this free propagation of these primordial photons is something which is a very important thing in this particular picture of the Big Bang cosmology. So if the Big Bang cosmology or the standard cosmology that we have now is correct, then we should be able to see these photons propagating. So they should be there, they are free and they don't interact, they don't go away. And that's what is called the cosmic microwave background. And people had looked at it, but its discovery, as I'm sure all of you will know, it was an accidental discovery by Penzias and Wilson. And in the next slide, we'll see that yeah, we can go to the next slide. So it measurements, actually later measurements, this was one of the first kind of map that we have from the cosmic microwave background explorer. This is the Kobe, where they had actually measured all these radiations coming from various different or all directions of in the sky, and then they realized, or they could actually show that it is a black body kind of a radiation with a temperature 2.78 Kelvin. So this is one thing which actually kind of gave us a lot of confidence in the Big Bang cosmology. And of course, the Nobel Prize, 2 Nobel Prizes goes with this at the moment. This is seen to be isotropic, homogeneous. When we say isotropic, in whichever direction we look at it is the same. It comes from not from a particular star or a galaxy or anything. It is coming from everywhere because it was the primordial one which actually was there from the universe. And it is homogeneous in the sense that it's the same amount whenever you look at. So in the next slide, we will see that although it is homogeneous and isotropic, it's not so very well. So there are some fluctuations, tiny fluctuations, small fluctuations. These are quite enlarged difference. It's a very, very small, tiny difference between uh, two different regions. Basically, you can see that blue and red or yellow patches have different temperatures. Not too different, actually, very small differences there. But this tiny difference is, or the anisotropy in the cosmic microwave background, was kind of established, and Kobe had actually indicated it. Later on, what's called the W map has given us a better picture, but the one that I have shown here is the latest from the Planck space probe, where they have clear in 2013. It has been taking data in 2013. It has actually given this kind of a thing, that there's a clear um, evidence that the temperature fluctuations are there, and then we could analyze it very well. So if you go to the next slide, we will see that analysis of this can be done, and then power spectrum analysis is done of the fluctuation. So delta T one can actually, so it's a function of the angle theta and phi, the directions in which you look at, and that you can actually write that function in terms of this spherical harmonics, and that allows you to actually look at it in terms of the multipole moment, and that gives a lot of information. So without going into the details of how exactly they come about, I mean, uh, it actually tells us that what is the energy content of the universe. And the first blob here, you can see that correspond to the first peak, and then that tells us that the total energy content of the universe is close to what is required for a flat universe. Okay, so whatever it is, then we can see from the measure the second peak difference in the second peak and the first peak, or amplitude difference in that will give information about the baryon content, so that you can say, baryon content in the sense that how much of the matter is there in it. So matter we call baryon because proton, neutron, etc. are called baryons, and that apparently is only 5%. And then the slope of the amplitude decrease from the first peak to the third peak, etc., and further on also. That actually gives the total matter content in this. Okay, so baryon is basically proton or atoms, etc., that is made of baryon nucleus. Electron is there, but since electron mass is very small, it does not really account much. So it is called the baryon content. It is the usual matter content, like atoms, and whatever we see, whatever we observe, all the galaxies, stars, etc. But the total matter content, according to this power spectrum analysis, is much more than this observable baryon content, which is actually 32%. So something like 27% is not accounted in the observable um, usual matter. So they are termed the dark matter, but it is matter, not energy in the terms of radiation. But then there is the rest of it has to be something like is the radiation, which is there, which is something like 68%, and that's called the dark energy, because I mean it's not usually, it is not in the form of matter or the usual radiation. So it is there to actually there is evidence of the accelerated expansion of the universe, which is different from this power spectrum, CMB power spectrum analysis. But that also says that's another evidence for the dark energy. That if the universe is accelerating, expanding. Not only that it is expanding at an accelerated rate. And this accelerated expansion is possible only if we have large amount of energy in which we don't know otherwise. So that's called the dark energy. So we can go to the next slide where we have, we can go to the next slide. Yeah. So the
Not this one.
I think this is fine. This is fine. So we have the we can actually get some more concrete information about the matter here, and that's if you look at the baryon number density, we see that you can actually forget about how it is arrived at, or if you can look at it later also. But what I want you to focus on is this: what is there in that red square. So the baryon to photon number density can be calculated from this, which means the number of baryons that is present corresponding to the ratio of the number of baryons to number of photons. So that's very tiny. That is very small. This matter, this particular information is an important thing for us. We will come to that soon. So in the next slide, we have, so this is what basically what we have kind of understood from our model of the universe, and also from the observations that we have, etc. But then we said the particles are created. How are we going to create particles from nowhere? So this has to be understood. That's where the particle physics, the particle dynamics comes in. So in quantum mechanics, we are all experts in the, I mean, you are all experts in the quantum mechanics and then deals with it on day, every day in your work. And we know that it works very well with atoms, whatever dynamics that atoms have, atomic spectrum, etc., can be worked out. But we don't really destroy any particles. The elements have the electrons and protons, etc., nucleus, etc., there, and that is not destroyed or I mean created there. It is the existing particles. We can change it from one atom to another atom, etc., but we don't really destroy it. We don't create it also. Quantum mechanics has no provision for that. Whereas we need to create this matter, and the special theory of relativity gives us a way of doing it in the sense that it tells that the matter can be, that there is an energy equivalent of matter that we can think about. So it's a famous relation, E is equal to mc square of Einstein. So we can go to the next slide. There we see that uh, quantum field theory. In the quantum field theory, we have so in the next slides. So yeah,
Not this.
no, next slide. This 16. Yes.
This is 17.
Oh,
It's not updated.
no. Oh, okay. So 16 it is.
I have to go back.
Yeah, you have to go back. And somehow it came. Yes, 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 yeah. In quantum field
It may
theory,
take some time.
yeah, sorry about that. So the in quantum field theory, which actually incorporates both quantum mechanics and special theory of relativity and put it in a framework which actually talks about how particles can be created and then annihilated. I mean, this is again there. If you look at closely the beta decay, what happens is that the neutron is annihilated or destroyed in a way, and or converted into proton, and electron is created along with, of course, the neutrino, another particle. So this cannot be understood by quantum mechanics, but we can actually understand it by quantum field theory. So there is a framework which we can clearly understand these things. So in slide 17, we actually have built a clear picture of how this all happens in a mathematically consistent way in quantum field theory, also incorporating what's called the gauge symmetry. I mean, I don't want to go into the details of that, but basically the gauge symmetry will tell us that for every interaction, like say the electromagnetic interaction, there is a mediator. So that mediator, in the case of electromagnetic interaction, is the photon itself. So when we are talking about an interaction between two charged particles, say electron and then electron, then it's they exchange these photons, and that's how they communicate and interact. It's not by action at a distance in another way. It's kind of we know the electric field and magnetic field. In the quantum picture, it is basically the quantized form of this electromagnetic field, and that's kind of what we call photon. And same kind of the analogy is taken to other interactions as well. So the weak nuclear interaction, which causes the beta decay, say for example, has the weak gauge bosons there to mediate these interactions. So here in the one picture that on below that we have on the left bottom, we have also called antiparticles for electrons. I mean, uh, they are similar to. I will come to a little more detail later or something. But basically, the particle and antiparticle can come together, annihilate, and they can give the radiation of the photons, and then these photons can be converted into different species of particles. So you can actually destroy or annihilate these electrons and positrons and create a different species called say muon and anti-muon. They are similar to electrons but not electrons. They are heavier, etc. So if we have enough energy, then we can actually create heavier particles. So creation of particles is possible, annihilation of particles is possible. All these things are well understood in the framework of quantum field theory, with gauge symmetry. So in the next slide, we have then, okay, so basically this is something which we are all familiar with. And as an only the last one, I just wanted you to just recap that the protons and neutrons are made of um, further smaller elementary particles called quarks. So, and basically at the moment that we think quarks and electrons are the basic elementary particles. Of course, we don't. I mean, at the levels that we have probed, they don't have any structure. They are not made of anything else. So they are the basic elementary particles at the moment. I mean, we don't know that at very much higher energies, whether there will be further structures or whether there is something called the string theory, which may be the right way of looking at it, where there's some other elementary structure is going to give rise to even the quarks or electrons, etc. But at the moment, all our explorations in terms of experiments and are consistent with this picture, where electrons and quarks are the fundamental or elementary particles. Okay, going on to the next slide. Yeah, so I mean, this is just that everything is made of this, and then for consistency, we need things like electrons, other things like electrons called muon, I just talked about, and then there is also a tau lepton, and there are three different neutrinos. And again, for quarks, there are different types of quarks, like there are six of them, and these, along with the photon and the weak gauge boson and what's called the gluons, along with, if you have heard of Higgs boson, I mean, whatever that is, which is basically a single spin zero particle that we have in the elementary spectrum. So this, what we have on the right hand side, is the entire is that is the list of all of the elementary particles that we have now. They are a handful, but all kinds of things that we see on Earth and outside Earth in the universe are all made of these and nothing else. In fact, it's only whatever terrestrial things are made of only electrons and two different quarks, the first two, down type and up type quarks. These three particles actually make everything that we have seen. So that is the beauty of this whole thing, that it is so simple in a way. So going on to the next slide, I think we can actually, yeah, how do we know all those things? Yes, so usually we want to actually smash things. I mean, if you, one way of looking at what is there inside is to smash these things. That's what exactly, okay, in the next slide, we have done with the protons. So going to the next slide, the protons, we have probed the interior of the protons by smashing it with very high energy electrons, and the results can be analyzed, and then this analysis basically tells us that there are structures within the proton. Okay, going on to the next slide, we have, yes, we we have the antiparticles as well. So these three particles, electron, U quark, up quark, and down quark, they make everything that we know of. The other particles are there for the consistency in a way. And all of these have antiparticles. The electron has what called antiparticle called the positron, U quark, U antiquark, and then the other one D quark also. So as you can see, the antiparticles have the same mass, but electric charge opposite. In fact, all other quantum numbers are opposite, in fact. Okay. So, electron has negative -1 in units of electron charge itself is -1, and positron, it is +1. Similarly, U quark in terms of the electron charge is 2 by 3, but U anti-quark is minus 2 by 3. Similarly, for down quark, minus 1 by 3 and minus plus 1 by 3. So let's go to the next slide. So these antiparticles are there, and that is the kind of thing which came out of what the Dirac's theory of quantum relativity, quantum mechanics, and quantum electrodynamics later on. But then without them, it will not be consistent. Okay, so let me stop at that without going into the details. But the various things can happen now. So when particles are created, they are created in pairs of particles and antiparticles. So electron is cannot be created just as electron alone, but electron has to be created always in pairs with the positron. One reason is that the electric charge has to be conserved. So there are various other things, other such conservations that forces in the theoretical framework that it will happen always like this thing. And similarly, quarks and antiquarks are formed in pairs. So going on to the next slide, we can also annihilate this, and then this also, when it is annihilated, also they are annihilated in pairs, and photons are created out of these annihilations, the energy, pure form of energy in a way. Okay, so the nucleosynthesis uh, um, and further structure formation would not have been possible then if particle and antiparticle were created, but they were together and they get annihilated and then again goes into this thing. So there won't be, these things wouldn't be left out to actually cool down and then form the structures or the nuclei, etc., and then the structures. So that's one of the difficulties that we would face now. So let's go to the next stage. But we know that the Big Bang nucleosynthesis has happened, and we are all here, all the structures are here. And in fact, Big Bang nucleosynthesis is basically understood quite well. Experimental information about the abundance of the primordial helium and hydrogen, etc., and even the lithium is very well measured, and we know the processes also now. And in all these things, the nuclei of heavier, not heavier, the proton is around, when the proton combining with neutron or other protons to form the nuclei of helium and lithium, etc. One of the important things in all this is the deuterium formation, and the deuterium formation is very crucial. How much of deuterium was there or formed is very crucial in all this analysis, and that depends very crucially again on the baryon to photon ratio. When we say here baryon, it means that only the particles. We don't have antiparticle structures in the universe, so we don't see that. We see only particles, nuclei made of protons, not antiprotons, and helium, not anti-helium, in the universe. So basically, it is the baryon number which tells that whatever is the baryon number minus anti-baryon number, or particle number minus antiparticle number, with the ratio of that with the number of photons. That is, so that is what is important here, and that has to be something like this. It is small, 6 times 10 power minus 10. This is what is needed for this to get the right abundance of the deuterium or the helium and hydrogen that we see in the Big Bang nucleus or the primordial ones that we measure. Okay, this is one important thing, that we have a particular or something, this ratio which we have to have. And we can go to the next slide and then see that uh, in the yeah. So okay, this is a cartoon just to show that matter and antimatter were there created in pairs, but somehow when they annihilate, etc., there has to be some imbalance between their numbers, and then one in a very billion should be left out. Particles should be left out. There will be one small extra particle content in this thing. And this is something which has not been understood. How this can be brought out is something which has not been understood well. And this goes by the name of Barium asymmetry of the universe. There is a slight asymmetry, and we have to understand it. So the present day particle dynamics does not really have a way of accommodating this. Well, there are different versions and different models, but we still don't know which one is correct or what exactly is the model that we will have. The standard model of particle physics does not have a way of getting this thing. So in the next slide, I think I have said what I have just now said. Um, yeah, so this is an very active area of research presently, and we don't really have a concrete idea about how to get this periodic symmetry of the universe. So going on to the next slide, we have another issue. As I said, when we look at the power spectrum, the visible universe, the matter, the periodic matter that we know we can measure is only 5%, and about 27% is dark matter. So this dark matter is also not accommodated in the particle dynamics in the present day. The standard model of particle physics does not really know how to accommodate or what is this dark matter thing. None of these elementary particles that we talked about just now uh, can actually fit in this dark matter characteristics. Okay, next slide. But then, yeah, so this cosmic microwave background is one way of accurately, in fact, measuring and quantitatively assessing how much of dark matter should be there. But there are also many other evidences. There are many other evidences. In fact, it has been there for a long time, from the beginning of the last century. So one is the rotation curve of the galaxies. So if you look at the rotation curve of the galaxies, and uh, and especially the rotational speed of the stars at the periphery of the galaxies, then if we go by the gravitational interactions, we expect that most of the matter is concentrated in the center, and then as you go to the periphery, then you don't really have any mass distribution there. There are a few stars, but not many. And these stars then would be seeing all the matter inside that volume that you can construct with the radius as the distance of this star from the center of the universe, the galaxy. And now we expect a simple calculation will tell you that the speed of this has to be kind of going down if we take the Newtonian gravity, which is going to work there perfectly all right. And if you take stars farther and farther away at the periphery, then we expect that the speed is going to reduce slightly. Uh, it goes as 1 over r. But what is seen observationally is that it is not the case. It actually goes kind of the same or slightly increasing in fact. So this is possible uh, if we have uh, if we have other gravitating matter there, which we don't see. So the observational matter, the matter that we see as in terms of the stars and the luminous matter, is not sufficient to explain this thing. There has to be something else. We don't see that, but its presence is indicated by this kind of rotational curve of the galaxy. So this is one thing, and in the next slide we will see that there is also what's called the gravitational lensing that we have seen. Distant galaxies, when we look at from Earth, is not seen as point source but as a ring, but usually it's not the full ring because of other disturbances. Parts of the rings can be seen, and this kind of gravitational lensing and is possible if you have huge mass, localized mass, in the on the way of this light from that distant galaxies to Earth. So there are enough evidences for this as well. And so going to the next slide, we then want to actually understand what is dark matter. There are a lot of, yeah, we can go to the next slide. So we have kind of various ways to try to understand what is this dark matter. We want to, if there is dark matter in our galaxy, and if we are all going through that, then there may be certain kind of setups that we can make to for this to detect this dark matter. So this direct detection experiments are going on for some years now, and what's done is these are very weakly interacting particles. Otherwise, we would have seen them. So the dark matter, by definition, one possibility, if it is an elementary particle, is that it doesn't interact very well with other matter particles. So, but they may be interacting very, very weakly. So, if you wait for sufficiently long time, then we may be able to see. This is the kind of in, uh, idea that we take. And so, these direct detection experiments look for interaction of the dark matter with heavy nuclei like xenon, and when they hit these heavy nuclei in a kind of volume, target volume, then they will actually have a recoil, and this recoil will actually, when they relax this, there will be light which can be actually identified, and then we can actually detect. So this is what the idea, and basically, so far we have not seen. Otherwise, it would have been there in the news, and then one of us would know. But that actually indirectly puts constraints on what kind of mass the dark matter particle could have, what kind of coupling it could have, etc. So these experiments are going on, and there are other places where we look at in the cosmos where the dark matter could annihilate themselves and then create energy like photons, and then people are looking for this photons otherwise not accounted, not coming from any star, etc. So that's called an indirect detection. Then there is an experimental facility called Large Hadron Collider that is also that is colliding proton and proton, and maybe we can create dark matter there. So creation of this thing in the Large Hadron Particle Colliders is another place that we look for dark matter. So we going to the next slide. I'll tell how much time do I have?
Uh, 15 minutes or so.
Okay, that will be sufficient. Good, thanks. So, so there is this Large Hadron Collider, which is situated in near Geneva, and it's one of the um, it's one of the high energy. I mean, in fact, it is the high energy particle collider that we have. So it accelerates protons to very, very high energies to 7 TeV, and it two such protons are collided, and this total center of mass energy therefore is 14 TeV now. And this there are various numbers that is given here. It is highly radiation prone age collision, therefore it has to be underground for safety reasons. 100 meters underground. Circumference of the ring is 27 kilometers. High magnetic field to bend these. I mean, the next slide I will show you some the dipoles that it uses, and other things. Like there are 4 experiments, 2 common experiment, general experiments called Atlas and CMS, and there are specialized other experiments also. Okay, so going to the next slide. So these are the dipoles. Just to show you that the thing, the magnetic field is very large, and then the technology involved is quite intricate actually. So the next slide we will see the detector complex. So it's huge affair. So at the bottom there is this red ring circle that there is a man, some person is standing there. So the scale is like huge compared to our size, and it's complex. So it has different layers also. So it actually has specialized parts to detect the particles like electrons, and then the specialized these things called hadronic calorimeter, where um, particles like pions or proton, etc., pions and then other these things, hadrons, things which are made of quarks are detected, and then there is also something called a muon detectors. So this is structured differently, and it's a complex detector. Going to the next slide, I think I have kind of. I'm just trying to give you a little bit of a flavor of what's going on. So yeah, so usually what happens is when protons are collided, I mean, it's a kind of a messy thing in the sense that the proton, as I said, it has three quarks. In fact, in quantum mechanically, you can even have gluons and then other small quark these things, but in pairs of this, etc. So it can continuously uh, create, and I mean, when they collide with each other, it's not that two of these will come together and two particles neatly come out. It's not like that at all. It's like a kind of come together and then kind of a huge uh, many different interactions go on simultaneously, and then all kinds of things will be there. And then from that, we have to actually separate out certain important events. Like, okay, so along with all these things that happens, there are two electrons coming out, or two muons coming out, things like that. So it requires a lot of modeling of the events that is happening, and a lot of electronics and computation and software support and everything is there. So the experimental setup and then the detection of these elementary particles or the reactions, and then the is a complex affair. But luckily, people have been, and we have been working with this for many years now, and various things are very well understood, and how to trigger if there is a particular event, what's called a two electrons coming out or two photons coming out, how to trigger that and to the computer and then tell it that yes, there is this particular event, etc., are all kind of very clearly understood now. And enough cross checks are also made. So if you go to the next slide, so basically then we can actually, yeah, so this is again saying that most of the time what happens is that these new particles that are created, we, now for example, the Higgs boson that you may have heard about, we don't really see it like electron coming out and interacting with particles. They are created, they are highly unstable. So these unstable particles decay immediately. So then when they decay immediately, we will see only the decayed particle, the product of the decay. But then we can reconstruct where these decay particles, I mean, where these particles have come from, and thus we get information about the original or the Higgs boson or whatever the parent particle was. So that is how it goes. So this, I think, in the next slide I have some more. Yeah. So here, basically, what we have is something went wrong with the background here. Okay. Anyway, so sorry that some of these things are not very clear. But basically, to the right hand side, if you look at, if you have some one Higgs boson, or some particle which is created, which decays to two photons. Say. And what your detector detects are these two photons. Now, how do we know that it is coming from a massive particle like Higgs boson? So for that, you can act one way that you analyze is this, that you measure the energy of these photons. You can also measure the position of this, and from that you can actually know what is the momentum of this. So you have information about the momentum and the energy of this. So if you put this together in the energy momentum relation, then you can actually get the mass of this. So this is called the invariant mass of the invariant in the sense that it is Lorentz invariant. So forget about it. But the mass can be reconstructed from the energy and the momentum. So when you together with these two photons give a particular kind of a mass, and that is the mass that corresponds to the parent particle that it became. So this kind of in that graph that you have, the lower one, the bump that you have is possible if you have such particle created and then decaying. If it was coming from various different places or not from a particular kind of particle decaying, then you don't really see this bump-like structure. So that is the kind of analysis that's done. This is called the resonant decay of this particle. This is this indicates that there is some such particle. Of course, this is not the only place. There are many different prospects of this. The Higgs boson can decay into other things also, and then we can actually we have to detect and we have to understand all of this, and they have to be consistent. For example, if the Higgs boson is decaying into something else, the invariant mass of that, or the mass of the Higgs boson reconstructed from that, should be exactly the same as what we reconstruct from photons. So these are independent measurements of this. So presently, we have the technology which is very kind of reliable, and then we know we can actually look for uh, new particles, various other dynamics, characteristics of various different particle dynamics that we have at the Large Hadron Collider and other places as well. So in the next slide, I will tell you what we do with the dark matter searches here. So in the dark matter, uh, in particle collisions, they usually, if it is an elementary particle and then the dark matter has its antiparticle also, then they will be created in pairs. But as we said, these particles are not going to interact with the detectors. So they will be missing. They will actually be not detected. There won't be any energy deposit or there won't be any momentum measurement. They will just be missing. Then if we have events where only these particles are there, we won't be able to detect them. So at the Large Hadron Collider, what's done is you look for these particles, the dark matter particles created along with, say, a photon. Okay, so such processes are possible in as per the particle dynamics. So once this happens, then we have one identifiable detectable particle, which is the photon. And we also know the initial energies, and initial energies have to be the same as the final energy. Energy momentum conservation will tell you that energy is. So from that, we can actually find out what is the energy of the uh, dark matter or the missing energy, and similarly the missing momentum. So that will allow us to also reconstruct the mass of this dark matter. Okay, so this kind of, and there are other strategies as well. So basically, people have been looking for this dark matter in particle collisions to understand it as an elementary particle, but so far we do not have any kind of evidence of presence of the dark matter or creation of dark matter. So this is the status that we have now. So let us go to the next slide and then see. Yeah, I think I am almost done. So essentially, the particle dynamics we have understood quite well at the level that we have been experimentally probing, and but there are a few things which are not understood well, and therefore we think that the theoretical model is certainly not complete, and we have to understand especially the dark matter and baryon asymmetry that we talked about today, also related to the related to understanding the universe. And there are other difficulties as well, called, if you have heard about the neutrinos, and there is a problem with generating the neutrino mass, which now we know experimentally has a mass. There, the Higgs boson, we have discovered that, and but there are certain issues with its mass, and then there is also other issue called stability of the vacuum in the standard model. So these are some of the issues one has to understand. So with all these things, um, the model is highly successful in the sense that it has actually been able to explain almost all the dynamics that we have seen at the subatomic level, excepting a few of the fundamental things that we have to understand and understand. Okay, in the next slide, I think that is my last slide. So the cosmology. So just to summarize this, universe, understanding the universe is connected very intimately with understanding the elementary particle dynamics. So it's in the early stages when matter was created, and the bound states of nucleosynthesis, etc., has happened. It is the particle dynamics which is more important there than the gravity itself. Of course, the gravity plays the biggest role by understanding the expansion of the universe and cooling of it, and then making the situation possible for the particles to come together. But how they are combined, etc., is dictated by the dynamics or the rules of the game that the particle physics dictates. Though we have quite a good understanding, but there are still some missing links that we have to understand, and it continues. So hopefully we will be able to fix many of these in the coming years, and the journey will go on. Okay, thank you. So that's kind of the end of this thing. The next slide is just the last slide that I have. So thank you all. Yeah. Okay. So I'm basically.
Okay. Thank you, Professor Poulose. Will you take few questions?
Yeah, sure.
So this session is open for questions or comments.
Yeah. Can I?
Yeah.
Hello.
Yeah, Anthony, we can hear you.
Yeah. Sir, we are actually the Detector process where we generally assume that neutrino mass is 0.
Yeah.
So that the energy equation is balanced.
Yes.
So once that is slightly violated by non-zero mass for the neutrino,
yeah,
what consequence will it have on the existing assumptions and other theories, as well as on the experimental results?
Yeah. Okay. Good. Yeah. This is, in fact, every experiment, as you know, has an uncertainty in the measurement. So in the beta decay, you are right. The Q factor, the energy available, entire thing can be also accommodated given to the electron. So some electrons actually come with large energy. So if you look at the maximum kinetic energy of the electron, then we see that the share of the energy that is taken by neutrino is very, very small, or it is consistent with zero. But usually what is done, it is within that experimental limit. So that actually puts a limit on the neutrino mass. You are right. So the neutrino mass cannot be large. It has to be very small. So in fact, beta decay, tail of that energy spectrum of the electron is what people have looked for. Even now, people consider to put a limit on the neutrino mass. So it is very small. The energy of the neutrino, the mass of the neutrino is 0.1 electron volt, and compare it with the electron mass. Electron mass is 0.5 MeV, so or 500 kilo electron volt. 500 or 5. How much? 5 into 10 power 5 electron volt. So this is very small, the neutrino mass. Because of that reason, it does not contradict any of those things that theory that we have. Only thing that we can warn the students saying that this is within the experimental limit, it is still can be considered to be zero. So that's all.
Okay.
Any other question?
I have one question. Okay, I am putting from. I have a question about that recently in an article I found that our Earth is moving in the debris of a neutron star. Right? Yeah, I think you might have also read that.
Yeah.
And if there is a very large density of, I don't know actually what is the dark matter thing, but if there is any density of dark matter maybe very high, then Earth is moving with a large speed and the galaxy itself moving with a very high speed, then is there any type of interaction or anything to happen? That is a doubt about that. And another question is that what are the main sources? Only is there any possibility high energy electrons and high energy protons are colliding? Is there any chance of the production of that?
Dark matter. Yeah. Okay. So firstly, let me understand the first question. You're saying that since we are moving in the dark matter, like maybe like in the other debris of the neutron stars. So now, what are the chances of detecting it, right? Yeah. So this is what the direct detection experiments are looking for. It assumes that we are actually moving through certain amount of this dark matter, and then if we are moving through this thing, then how do we detect it? So usually we can't detect. For example, if you look at the neutrinos, I mean, this is now we have ample evidence for the existence of neutrinos, and neutrinos are created in sun, and then it comes from sun, radiates from sun. So there are large amount of these neutrinos which are coming, and passing through us. Not only passing through us, even now as we are speaking, it passes through the entire Earth without interacting. So they are very, very, very feebly interacting things. Dark matter is expected to be even more feeble compared to the neutrinos, or at least at that scale. So they will pass through us. They will not interact with us. In normal matter, usually, unless there is a large amount of this thing it is going. So the probability for it to interact with small bodies of this thing will be very small, so one has to wait for now. So what is done is, in the specific experiments, they have a controlled target of xenon, liquid xenon, and that's in large quantity. So they then look at this with specific photon detectors that there is some light coming out apart from the background, uh, which can be accommodated to the recoil or the interaction of the dark matter with the xenon. So this is actually a very difficult experiment because this interact very feebly. So what you said is right, that since we are going through this dark matter density, and because of that we should be able to detect it. And the lack of the evidence or no observation puts limits on its mass, its interaction strength, etc. So that is what is. So the second one was
Yeah, high energy electrons, high energy.
yes. Producing. It is again similar. Like what it is in principle, it is possible. But again, because of the weak interactions, very small weak interaction, probability for it to actually happen is very small. But it's possible. But we won't be able to really detect it because it is so rare, and everything has a background, right? So the background is overwhelming. For example, electrons and positrons are annihilated, and then neutrinos can be created, and they are also missing, etc. And then we don't. I mean, it has in a controlled experiment, it is easier rather than looking for it in the cosmic thing. There won't be unless the probabilities are very large there. So, but still, what is more probable is this annihilation of the dark matter, because they are in some kind of density, and emission of the photons. Photons not accounted otherwise, not coming from other sources. Photons not coming from other sources, but possibly from the dark matter. People are looking for this. This is basically known as the indirect measurements. In fact, a couple of years before, there was some news rumor that yes, there is some detection of such a pair of, the new photons, which cannot be accommodated otherwise. About 130 GeV or some such thing mass. But I think more precise measurements actually said that that is not the case.
Okay, thank you.
Okay, there are two questions in the chat box.
Yeah.
From Dr. Ravi Kumar, and he asked, does the standard model require dark matter or dark energy? That's the first one.
Okay. The standard model of particle physics does not accommodate that. It doesn't have that as a part of it. But the dark matter candidate should be there as part of the particle dynamics. Yes. And dark energy is even is slightly different. So it is not thought to be as kind of presently we don't really have any way of thinking about how to accommodate or think about dark energy within the particle dynamics. Rather than that, it's thought about in terms of gravitational cosmological constant and then other distinct ways. So it may be slightly a different mechanism or different way to accommodate dark energy. But dark matter certainly very, very possible that it can be accommodated as an elementary particle. It's like neutrino or some such thing. Neutrino itself is not sufficient. It would have been a good candidate, but what is the problem with neutrino is we cannot form local structures. It is very, very light. It is its mass is very, very small. So but we have enough evidence that dark matters are concentrated in kind of, it is localized. It is localized around the galaxies, etc. So there are, that is not possible. they are particles.
Ravi Kumar? Ravi, you
Yeah.
can ask the second question yourself.
Yes, I mean, okay. The specific question was that actually the localization of dark matter,
Yeah.
because what we in the galaxy dynamics we say is that, I mean, galaxies are formed in the dark matter halos. So,
Yeah.
for our nucleosynthesis, do we really need such a scenario?
Okay. So, not nucleosynthesis. There are two nucleosynthesis. One is the Big Bang nucleosynthesis, which happened in the early times.
Yes.
Yeah. So there you don't need that. That nuclear synthesis is very, very well understood with the existing particle dynamics. So the dark matter itself is not really needed there. And the later on now, if the dark matter would have been there also, that wouldn't interfere with the nuclear dynamics because they are very weak. Now, but what happens is that later on, when the large-scale structures are formed, gravity is more important compared to gravitational interaction become more important. For example, the formation of the galaxy, etc. If the particle dynamics itself is not crucial there in the formation of the galaxies, of course, accepting the nuclear reactions inside the stars. But apart from the nuclear reactions in the stars, the gravity is the dominating part there in the galaxy formation or supercluster formation, etc. There, the dark matter, because the dark matter is gravitating, they are very important there. So, not in the nucleosynthesis, but in the large scale structures. Yes.
Okay, thank you. The second question was about do we have any predictions on decay times for say particles? The standard particles, the protons and the electrons, like stable particles. Okay, do we have any for those things from the standard model? Why I'm asking is that, I mean, just thinking of the universe expanding, and do we need to think of some kind of a big crunch or something else what can happen later?
Okay. So the question is proton decay. Say for example, what is the prediction of the standard model? Is that one question?
Yeah.
Prediction of the proton decay.
Proton.
Within the standard model, proton. Within the standard. Yes. So within the standard model, proton decay is very, 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 very small. I mean, it is forbidden. So it can happen at a very, very, very small, and that, according to that, the mean lifetime of the proton is much larger, much larger than the age of the universe. So, and electron is also similarly. I mean, it doesn't. The decay is actually prohibited through what is called the baryon number. Baryon number conservation. So the baryon number, there is no other baryon particle, baryon bound state than proton that it can decay to. So any decay of proton will be violation of the baryon number. Similarly for the electron also, there is no other electron which is lighter than the electron. So it cannot. So there are within the standard model they cannot decay actually. So that is okay. But when we actually go beyond the standard model, as I said, there are enough reasons that we should think beyond the standard model to accommodate the neutrino mass, to accommodate the dark matter, etc. So there are some of the grand unified theories which predict neutron proton decay, and there one has to be more careful, and one has to accommodate. I mean, one has to arrange things so that the mean lifetime of proton is larger than the lifetime. I mean, the age of the universe. But within the standard model, it is not a problem.
Okay, okay, thank you.
Okay. Any other questions? Seems no. Krishnamar sir, are you asking some question?
No, I'm sorry, I don't have any question.
Okay, I saw your mic.
Yeah.
Okay, if there is no questions, let us thank Professor Poulose for giving excellent talk on this platform, and we are very thankful to him. So I invite him to come to visit our department whenever he is coming to Kerala sometime.
Sure.
Always our invitation is valued, and you could visit our department. And thank you again.
Thank you all.
Thank you. I also thank all other participants for this evening lecture as success. Thank you all.